morning, everyone. My name is Jane, and I will cover the paper towards an in-context LLM-based approach for automated definition of model views. I am a PhD student, and this paper was written by me with my supervisors Hugo Bruneliere, Massimo Tisi, and Gerson Sunyé. Here is a quick agenda of a presentation, so I will start presenting a bit of the context and the background of model views and EMF views. I will go to the problem through using an example that I got from the tutorial, the EMF views tutorial. Then I will go to show a bit of our proposal solution that is using LLMs, and I will finish with the contributions and potential future work. So let's start with the context and background on model views and EMF views. When we are working on very complex engineering systems, it's very often that we need to use different models that are written with different language, conforming to different meta models. Often the software engineer will use EML to represent the software. Some other stakeholder can use SysML to represent other parts of the systems. We can use BPMN to represent the business, and even some DSLs to represent other specific parts of the system that we are working on. The challenge arrives when we need to combine all these models together somehow. We are trying to create a single modeling artifact that can somehow represent the whole system, or at least part of the system, hiding some information from everyone, or highlighting some information. This is what we are calling here as a model view. One potential strategy to cope with this challenge is to create a ViewPoint. So we create a ViewPoint based on the meta models that work as a meta model to this model view. EMF Views is a tool that was created with this idea in mind. It is a tool that is used to create model views over EMF compatible models. We have the tooling works in a way that is scalable because we don't copy all the elements of the models to the model view. We only have some proxies that point to the actual elements in the model. What is the problem that we are trying to work over here? To show the problem, I will use an example on books publication. That's an example that I got from the EMF Views tutorial website. This is a very straightforward example, but it already showed to us some challenges that we can work on. So on the left of the slide, I have a very simple meta model that represent books. So I have books and chapters with some standard properties, and on the right of the slide I have a meta model showing a publication, also with some standard properties like the title, the name of the author, the year of publication, and so on. When we are using EMF Views, the tool comes with a special DSL that is created to help us to develop this ViewPoint. The language is called ViewPoint Description Language, or VPDL. And in this slide, I have an example showing to you how we can combine books and publications in a model view. You can also access this example on the EMF Views tutorial. So how we create, as you can see, look into the language. It's a SQL-like language, so it's pretty similar with a database view. And we can define the view name. We can define the features. It means the properties that we are selecting from the models that we want that appears in the view. We also have this join construct that enables us to actually combine two different concepts from each model. We need to define, based on the RI, the contribution meta models, and we also can define the rules that we will compute this association. So for each join that we defined, we need to have a correspondent rule on the where block that will calculate how we will combine these two meta classes. In this case, I have a combination between a publication and a book, and I'm matching the title. So when the title is the same, I know that they should be combined in the view. I was able to create this ViewPoint because first I know VPDL. And I also know details about the underlying metamodels. But what we are trying to achieve here with our proposal is what happens when we have a very diverse team that does not know necessarily everything about VPDL, or they don't know everything about the models. We are trying to create some kind of tool, some kind of approach that can help the engineers to reduce the workload of the engineers, and also provide some kind of automation. So at least a starter point, how we can start the work with some kind of automation. One idea is to use LLMs. LLMs, as you may know, are large language models, a special kind of neural network that is based on the transformer architecture, and it was designed to process textual data. It has its breakthrough 1 or 2 years ago, and it can be used on a lot of tasks like text production, translation, text generation, and also text reasoning. Okay, so when we are thinking, okay, we have this problem of how to combine models in a model view, we have the language, what's the most straightforward approach that we can go? Let's go to ChatGPT, ask them, here are the PlantML versions of my metamodels. I want to create a view that combines books and publications. Give me the VPDL code. This is the result I got on a specific chat session that I had. As you can see, it makes sense, but not VPDL code. It do not look like VPDL code. And why it happens? Because ChatGPT, actually the GPT model that's in the background of ChatGPT, does not know VPDL. It probably does not part of their training data. It contains some hallucinations, so what is very common when we are using LLMs. It's syntactically incorrect. It is not VPDL, neither any other language that, at least the language I know, or a language that we can use. And also in the pairs that, in the combination of the classes they are proposing is not exactly the classes that we are expecting. The numerical data is on the paper if you want to see. So our solution is to somehow try to use LLMs to solve this problem, solve problems partially generating the view description with the minimal input from the engineers. On this slide, I have a diagram with our approach. We are relying here on prompt engineering first, especially chain of thoughts and few shot prompting, that are two techniques that are getting some traction on the LLM community. We are counting also on the decomposition of the problem. As I showed to you, the VPDL contains 3 very well-defined blocks. So we can try to decompose the problem of create a VPDL code in 3 different problems. We are trying to do not use retrieval augmented generation, neither fine-tuning. What are the 2 other potential techniques to solve the same problem? And we are using the same LLM that is used on the ChatGPT, the GPT-4o. Let us go step by step on our problem. As I said before, we are trying here to solve this problem with the minimal input from the engineer. So the inputs that we are expecting on the first step is just to receive the e-core metamodels and small, or at least small enough, a small description of the view. So the user does not need to know necessarily anything about the VPDL. They just need to provide a textual description of what they want to see in the final view, that we are calling here a user view description. The first step that we have is a pre-LLM step. We just convert our e-core metamodels to use the PlantML notation. We did this in this way because of based on our own experimentation and also in other papers that deal with this problem, we know that the LLMs understand better PlantML notation in comparison with the e-core or XMI notation. And then we go to the Next step, that's the first LLM step. So what we did here, we create these prompt templates. Prompt templates are very long textual instructions that will guide the LLM to solve a specific problem. So in our case, we create 3 prompt templates. One just to define what elements will be selected by the LLM. Another just define what pairs of meta classes will be combined. And the last one to define the rules of associations, how combine these models. In this slide, I have an example, just the first lines of the join prompt template. And what we did here, we inject the information that comes from the user, the core metamodel, the plant ML metamodels in this case, and the user view description inside this prompt, and then send to the LLM. We are able to ensure that the LLM will answer us with a textual output because it's an LLM, but we can ensure that it's a JSON response, and we can then analyze this response. What we create here, we create a new component, output parser, that will analyze this response, this JSON response that came from the LLM, and check if it will if it respects some constraints, like if the meta classes that they are proposing really exist on the meta model and things like that. So we can iterate for each prompt template that we create. We can iterate sometimes to ensure that the response respects these constraints, and also we can iterate for each one of these 3 tasks that we define: one for select, one for join, one for the where. It's important to note that the engineer that are using our solution does not need to edit, to change these prompt templates. The only thing that they need to provide is the metamodels and the description. So this is the VPDL code that we use as a reference. As you can see, that's slightly different from the previous one that I showed, because here I have 2 relations, but the idea is the same. We are still combining books and publications as I showed to you. This is the reference output, and this is the final output of our approach using LLMs in the way that I explained. We can see that the properties that the LLM propose are okay, they match exactly the properties that we are looking for. On the join block, we can see that we have the 2 relations. We have the LLM get 1 relation in the wrong order, but it's almost the same relation, the same relation that we are expecting. And on the where block, as you can see, we are not asking the LLM to generate OCL. Actually, in the EMF Views, we use ECL, but we can generate ECL code or OCL-like code to navigate in the models and create the combinations. Instead, we are asking the LLM to generate natural language explanation of how to combine the meta classes, and the engineer will be responsible to translate it to ECL in this case. So for a moment, let's concentrate on the select and the join. So for the join, we calculate here the precision and the recall of our approach. As I said before, we have one exact match of the relations and one match but in the wrong order that we consider here incorrect. And for the selected block, for the properties that we are asking the LLM to select, we have an exact match in comparison with our reference code. I also want to highlight that we have 100% syntactically correct code. This is a VPDL code, or almost. It's a draft of a VPDL code. Even if it does not compile, it will be fairly easy for an engineer to convert it to a final VPDL code. And for the where part, since we are not generating the expressions, we are analyzing it qualitatively. So we know that from a human evaluation, it's satisfactory enough. And to also use LLM to analyze our final response, we are using an approach that's called LLM as judge. It's a approach that also getting some traction on the LLM community when we ask another LLM on how hard it is to go from this generated code to my reference code, and we have a scale here, a kind of a grade. So just checking the quantitative analysis of the join and the select, together with this example that I showed to you, we also select 3 other views from the literature, 3 other views created with VPDL code. And I want to highlight again that we always have syntactically correct the code, even though we don't have the best results on the precision and recall on all examples. You can also check the numerical evaluation on the paper. So I can start to conclude what we have as contributions on this work. On the technical side, we are trying to provide an in-context approach. It means that the user does not need to give any, does not need to have any special knowledge to use our approach. The LLM don't need to be pre-trained on the VPDL code. We are not expecting that it to be fine-tuned. And also, we are not expecting to use retrieval augmented generation, because both fine-tuning and retrieval augmented generation can have can be expensive, and then can also bring other problems to the scenario. And we are using here VPDL as an example, but we can see that the same approach has also potential applications to other modeling languages. On the LLM side, on the application of LLMs for engineering problems, we are showing the feasibility of the use of LLMs to draft model views. Again, in the example, we are using VPDL, but we can think on any other language to create model views. And we show something that show something that it's already on the standard knowledge, that the decomposition of the problem helps LLMs to better reason on the problem. So small problems are solvable for the LLM, and we can combine the solutions of each step in a final solution. We implemented our approach with a prototype using open source tools, more specifically LangChain. It's an orchestration framework for LLMs, and PyCore to deal with the core details of the metamodels. And we also use off-the-shelf LLMs. For this experiment that I showed to you, we are using the GPT, but thanks to the LangChain, it's flexible, we can change and use other LLMs that we may want. And we know that using our implementation, we have a good starter point for the engineer, even without deep knowledge about the underlying metamodels. For future work, the challenge that we can see here, on the use of LLMs to solve this kind of problem, our approach is somehow a single agent approach. We have one agent that thinks on the full problem. And we are seeing the machine learning, the LLM community, that what is the future looks like. We will work much more with multi-agent approach, which means that we will decompose the problem, but instead of solve the problem just using the LLMs as I showed to you, we will give these small problems to very specialized agents that will solve one part of the problem per time. With this multi-agent approach, we can also think on integration what we call the human in the loop. It means that we can provide a more interactive approach. Now, with using our tool, the user provide the e-core metamodels and the description and have the VPDL draft at the end, but we can think on something more interactive, like a chat. And we also intend to test using other prompt engineering techniques. As I mentioned before, the prompt templates are created by us. And the prompt engineering is a very empirically engineering. We need to try and a lot of possibilities. It's natural language text. We need to instruct the LLM to behave in some in some way. So we together with the chain of thoughts and the few shot prompting, we can try other prompt engineering techniques. On the MD side, on the integration of everything on the modeling workbench, we can first think about a better integration between our solution and the EMF Views, the Eclipse workbench, because now they are splitted solutions. The user needs to copy and paste the draft to the EMF Views to use. And we can also try to find relevant data sets of model views. As you see now, we have 4 views that we are using to test, and also with these 4 views, we have some troubles to use good metrics. We are using precision and recall, but with relevant data set with more views, we can think about use other metrics like the PZK. That is one of the metrics that has been used to analyze code generation. That's it. Thank you. I'm open to answer any question, and on the QR code you have access to the code and artifacts of our work.
Thank you, James, for the presentation. Questions?
Thank you for the talk. It was very interesting. So one of the things I noticed is you did manage to have the LLM generate syntactically correct views and so on. But I think I also saw in one of the slides, I think it was slide 19, where there was a bit of EMF views where it just had arbitrary natural text in it, was it? Which I guess you had to iterate through over it, right? So there were bits by on, right?
Yeah.
So I was just wondering if you had looked at things like output grammars for LLM. So this is something that it's not really a thing on GPT-4, but llama.cpp has output grammars. You can give it a Bacchus noun form of the grammar of your language, and it will limit the available tokens. So instead of asking, random words and so on, it will just say, well, according to the grammar, you can only pick among these ones. Which one do you want among the ones that are available? Have you looked into these?
Thank you for the question. Indeed, we look to this kind of approach. This is I didn't include in the future work, but it's somehow a natural continuation of what we are trying to do here. Exactly because we know that even with standard GPT, we are capable to generate OCL-like code. They are capable to generate something that looks like OCL, but you are right, to generate something that is more formal, we need to provide some grammar. And I was not aware about the Llama capabilities to do it, but thank you. Yeah, but indeed, to give a grammar to the LLM is indeed something that we need to try in the future.
Yeah, because it might be that one option might be to make saying, okay, I actually know a little bit of the creating arbitrary text, right?
Yeah. One challenge that I can see on the approach, I didn't try, but I can see because a grammar can be, if you give the grammar to the LLM, it will be a long textual file. And we are in our approach, we are giving to the LLM long files that represent the metamodels. Yeah. So with the metamodels plus the grammar, maybe we will have troubles with the context window of the LLM.
But it's actually not part of. It's actually the configuration of the LLM. So I can show you a link maybe later during the break. I can show you a little bit of where to look at. Okay, but it's more a prompt to the LLM.
Okay. So this one I was not aware about.
Yeah, I can show you to you later.
Okay, thank you.
I was wondering about how many examples did you use for the few shot approach?
We have these results that we have here. I'm using 2 examples for the few shot. But But we, on the experimentations, if you look on the artifact, we have the option. So when the user will run, they can choose between one and five. 1 and 5 examples per view. It has a problem because with 5 examples, the problem that I mentioned right now also happens. We have a pretty long textual information that sometimes does not fit on the context window. But yeah, between 1 and 5. These results are 2.
Okay, perfect. And what about which technique was better, like few shot or cut? What was your experience?
Yeah, actually, this is a combination of both. It's a few shot chain of thoughts. No, yeah, few shot chain of thoughts. But I think that the few shot give us better results even without the chain of thoughts, even without the instructions of chain of thoughts. So the few shots is better.
Okay. And could you elaborate a bit more about the data set used for this study?
Yeah, so we got some we got some views that we know from the literature. We have 4 views that were used in other papers. So what we did here, we have this reference code that we have the final VPDL. We extract the explanation of the view from these papers. So very naive explanation of each view, and we just give to the LLM. This is our idea. This is something that I didn't mention about, but we know that this is something that sounds standard for who is using LLMs. Better instructions give better solutions. So we know that our prompts are not our prompts. The user prompts are not the best ones because we are just extracting them from the papers. When we try to improve this prompt, we reach better results. But we are trying to be fair and also be reproducible. So this extraction looks like a very reproducible approach.
Okay.
Yeah, but the data set contains the core metamodels, the user description, and the reference VPDL.
And was it for the same domain?
No. They are the 4 views are each one of different domain.
Okay, perfect. Let's thank James again.